Okay, good afternoon to everybody. I will now start the last day of my lecture, and I will begin to finish the topic that I was considering yesterday night, which afternoon for you, night for me, which was a turbulent combustion noise. And based on the monopolar sound emission, which is a well-known problem in acoustics, saying that the total intensity, acoustic energy radiated per unit time is related to the square of the second derivative versus time of the volume of the fluctuating volume of a small solid body was the size is much smaller than the wavelengths of the acoustics. Here, okay, where is my okay, I all the time lost my pointer. Where is my, oh, here it is. You know, the total intensity, where VT is a fluctuating volume of a solid quantity, let's say a sphere, for example, that is fluctuating, the radius is fluctuating, so that the volume is fluctuating. And it turns out that the sound, which is the total energy radiated per unit time from this source is written here. This is a famous result in acoustics. Now, concerning the sound generated by a turbulent frame, which is sketched in this picture on the top of my slides, where a premixed turbulent frame is stabilized at the rim of a Berger. The derivative of the velocity of okay, excuse me. The derivative of the equivalence volume, the derivative with respect to time of the equivalent volume is simply the mass flow rate of burned gas divided by the density of the burned gas. This mass flow rate is easily expressed in terms of the surface, instantaneous surface of the flame, the integral of this on the surface of the elementary volume of the surface multiplied by the normal velocity of the front plus the velocity of the gas, the burned gas relative to the front, which is simply this expression. Now, a similar expression is obtained for the mass flow rate of fresh mixture coming out from the tube. It's simply you have to replace the density by the fresh mixture density and the velocity of the gas relative to the front in the normal direction, replacing UB by UL and integrating over the surface. This is the mass flow rate of so elimination of the velocity, the instantaneous local velocity of the front in the laboratory frame, you obtain this expression here, where you have that this term is equal to this term plus UB minus UL, but these are constant quantity because we assume that the inner structure of the flame is not modified. So the burn gas, the flow velocity relative to the flame in the normal direction is not modified from the planar structure. So it is UB minus UL times the integration, which is a constant, times the integration, times the surface. Okay, now if you consider that the mass flux, the max flux, the mass flow rate of fresh gas, which is flowing out from the tube is a constant, neglect its fluctuation because of the flight turbulence. This is very small, is quite negligible compared to the fluctuation of the second term, which is here. So that when you take the second derivative of the volume, you may neglect the variation here, and you obtain this expression here. Now, applying this general formula, this general expression here, you obtain this, because applying this into this, you obtain this, and this develop in the frequency. This give the integral of the autocorrelation function of the time derivative of the derivative versus with respect to time of the total surface of the flame, ST. Okay, and this is the power, the spectrum of the power intensity which is radiated by the flame. This is so. What has to be kept in mind is that this spectrum, power spectrum, is related to the autocorrelation function here of the fluctuation of the surface. This is a simple result, which is useful as so. I have rewritten here the results in the next slide, and now, assuming that we are in the regime of a strongly corrugate regime, for which the Kolmogorov scaling is valid, it's not difficult to compute this surface fluctuation and this autocorrelation function, and the final result that you obtain when you take into account the result for the flame surface in the strongly corrugated regime in the inertial range of wavelengths. So you obtain directly from this equation, you obtain the power spectrum of the total intensity of the sound, which is predicted to vary like the frequency by the inverse of the frequency to the power 5/2, which is related to the dimensional to the scaling law of Kolmogorov scaling law and to the dimensional fraction of the flame. So this is straightforward. You find the detail. For example, in my book with Jeff Servi, the detail is given to go from here to here. It turns out that this is a very good surprise, that it is in total agreement with experiment, 78 experiment. It should be. Oh, well, that's nothing. Okay. Okay, it is in total agreement with the power spectrum measured by these Russian people in 1978, which you see here are the data from these people for very large, for experiment with very, very large burner. It works, it's not so bad for 2 order of magnitudes for scaling for frequency ranging from 10 to the 2 to 10 for the 4. So, you know, this exponent is not so bad. So this is good, but but when more recently the noise emitted by a blowtorch, it turns out that the experiments that have been developed in our lab shows that this noise, this intensity of the noise, is 2 orders of magnitude than predicted by this analysis. So, you know, by this analysis, when you look to this, and when you compare with a blowtorch, you find that it does not agree at all. And this is a very interesting point. And it was really well understood by Jeff Sirby, let's say 20 years ago. The result is the following. Why it is quite different? It is simply because the noise is not resulting from the direct interaction of the upstream turbulence, you know. Where I have to put here again. You know, the upstream turbulence here, which flows out from the burner, from the tube. This gives you this corrugate flame. Okay, this is direct interaction. In the blowtorch, this turbulence is very, very weak. But it turns out that because of the intrinsic instability, flame instability, for essentially the Darius-Landau instability, as shown in this picture, you know, even for a very small turbulence here, you have an amplification here, which is due to the along the flame, which is due to the intrinsic instability of flame instability. And this, excuse me, that's too bad. Okay, this was an excellent result, which was
Professor.
Yes.
Slides are not visible actually.
No, I will be back. Okay, I will be back to the picture. All right.
Yeah.
Okay. You know, this excellent result. Where it is? Wow. Where is it? Okay. Was obtained by Jeff Sirby, let's say 20 years ago, and well explained in this article. So this shows clearly that the turbulent flame problem is a very, very difficult problem because the condition for which the strongly corrugate regime, that is the only regime for which we have some correct prediction, this is very hard to obtain in a laboratory experiment. Okay. Now, I will develop the two last, the rest of my lectures is now will be focused on detonation wave in gaseous mixture. So I skip completely, I change completely topic. Okay, cool. So let's go to this topic. So this is finished. So let me start with, okay. Now the next lecture concern the supersonic combustion waves. And the first lecture on that topic is quite elementary. It's, I am going to just recall, where is my point? Some background. So let me start with some elementary background concerning combustion, detonation. Okay. Before to talk about detonation, I have to recall a few elements concerning shock waves. The simplest configuration to understand what is a shock wave is to consider a flow in a tube, and the end, and one end of the tube is a piston that moves with a constant velocity relative to the laboratory. Start moving at time equals 0, for example. So initially the gas is at rest, and after the column of gas should get a velocity equal to the piston velocity. Okay, so how the infinite column of gas gets this velocity? It obtains this velocity through the supersonic propagation of, let's say, a discontinuity where the gas is at rest in front of it, and the gas is in motion behind it. Now, this is the same picture in the referential frame of this shock. And this shock, this discontinuity, is what is called a shock wave. And you have here, this problem was discussed at the beginning of the 19th century by people like Poisson, the French scientist, and Riemann, the German scientist, and at the end, the last, and Hugoniot, who is also a French scientist, and the English scientist Rayleigh at the beginning of the 20th century. So it took, this shock wave took 1 century to be understood, in fact. And this is something that the students, that the people have to keep in mind. And the thickness of this discontinuity is microscopic, in the sense that the thickness is few mean free pass. So it's a microscopic quantity, it's not macroscopic. And let's consider the shock wave as a singularity of the Euler equation. This is before discussing the physics of the inner structure of the shock wave. Let's work with the Euler equation and look if there are solutions that are singularity as, for example, a discontinuity that propagates in the flow. Okay. And to understand this problem, it's good to start with a much simpler problem than the Euler equation, which is an hyperbolic equation, which is written here. Well, you see, it's except for the pressure term, and except here for the, it looks like an Euler equation. So this equation is an elementary model of an hyperbolic equation explaining the formation of discontinuity. If the problem is the following: knowing the profile of the distribution of velocity at the origin at time t equals 0, what is the solution of this equation. Okay, that's the problem. There is a very simple case. The case is when this function a here, au, is constant. It's a equal a naught. It does not depend on u. Then the solution is trivial, and it is a propagation at constant velocity a naught of the initial profile without deformation. Okay, this you put this in this. Excuse me. You put this in this expression for a equal constant, and this satisfy this equation. So now, what the solution is when a is a nonlinear function of u, where the variation of a with u is non-zero. And this problem, it's a purely mathematical problem, which was solved by the famous physicist or mathematician. It is difficult to separate physicists from mathematicians in the 19th century. You know, Riemann. He is considered more than a mathematician than a physicist. But it turns out when you read the original papers of Riemann, that he knows very well the physics. So he developed a method for solving this equation here, let's say, by the methods of, method called the methods of characteristic, invented by Riemann, in fact. It turns out that the solution is conserved, that u is constant along any trajectory such that in the plane xt, excuse me, in any trajectory such that the derivative of x relative to the time is this velocity au. You know, if you know the solution of this equation and call that xt, it's easy when you use this relation and you put this solution in it, it's clear to see that the total derivative of u is constant relative to t when you derive this function u through t here and through t, which is here, and you use this relation here. So, and it works, this is the solution. So, this is a Riemann problem. This is the methods of characteristic, so that it turns out that if u is constant along this trajectory, which is called the characteristic xt, if u is constant, because a is a function of u, a is also constant. So this term here, au, is constant. Good. So it's such a way that knowing the initial condition, you know, knowing the initial condition, where a equal a naught, for example, that's the definition. This is a trajectory which is called the characteristics, because a is constant. So dx over dt equal a naught, and so the solution is a linear function of time. So what is called the characteristic are straight line in the plane xt, and where u naught here, for the original u naught is the value of u at function at for a naught, which when you inverse the function au. Now consider the case where the speed a nu, where the function a nu increase is positive. That is, dA over du is a positive function. So you consider the case of this equation where this function AU is an increasing function with u. So if you have an initial distribution like that, you have an initial distribution A naught of the velocity A. And because the part of the profile of the flow velocity where u is large propagate faster than the part of the velocity profile where the velocity is smaller, because A is an increasing function of u, it's clear that the top here is propagate faster than the base here. So at one times, you have what is called a wave breaking. And this corresponds to the fact that the characteristics are intersecting. Okay. And this here are the trajectory of the characteristic, and it is not difficult to find out what is the time lag after which the singularity appear. You know, you just consider this equation relation here, excuse me, and such a way that the partial derivative of x divided by the initial position is this term is 1, and this term tells you it is t time. So now, if you inverse the derivative dx naught over dx is 1 over 1 plus t multiplied by the gradient here. And so du over dx, which is what you are looking for the time at which, excuse me, the time at which the slope become infinite. So you look for the time at which du over dx, starting at initial consideration, initial time like a bump, you will obtain a vertical slope, so that the next step is a wave breaking. And so you look for du over dx becoming infinity, and using this expression, you find immediately that the divergence is obtained when the denominator goes to 0. So this gives you the time. And now this, the shortest time for which corresponding to this equality is a time where the slope here, correspond to the inflection point. So you obtain that the time of wave breaking is simply the inverse of the maximum of dA over dx0, and this maximum is at the inflection point on the decreasing side of the initial bump. So you find immediately the singularity. So now the second point is the following. Does this solution, because we are thinking about the first slides I showed to you, where you have a discontinuity propagating with a constant supersonic velocity, okay, which is a shock. What is a shock indeed? A shock wave, excuse me. So you begin to write this equation in a conservative form, in such a way that you introduce the function, the flux gu, which is simply the integral of AU. And the question you ask is the following. Are step functions like the one which is described, which is sketched on the picture on the right-hand side here, is a step function propagating at constant velocity solution of this equation. This is a question because you would like to understand the shock wave of my first slide. So you change variable, you change changing because the constant velocity is an unknown. You find this and you obtain simply the expression of, more exactly, you obtain an expression, a simple expression of this. Here, here I put U minus. In that case, the GU minus is 0, but you can put any initial value here. So arbitrary value in the lower bound. But okay, so this is written for any lower bound value in this integral. So you obtain this integral. You say you are very happy. You say, okay, there is a solution. There are solutions in the form of step function propagating with a given way, and you obtain the velocity. It turns out that this problem is not well posed, because if I multiply, it's enough just to multiply the basic equation here. Where are you? Excuse me. I just okay. If I multiply this by any function fu, I will find a different velocity of propagation, and this is just it is written here. So, in a sense, this problem is not a well-posed mathematical problem. It is a ill-posed problem in mathematics. So, let's say that looking for solution propagating of a constant velocity solution of this equation is not a well-posed problem in mathematics. There is an infinite number of solutions like that. So this is what I have recalled here. It turned out that if you add a small dissipative term on the right-hand side, you know, du over dt, and if du over dt equal epsilon du square, the second derivative for u with respect to x, this is a diffusive equation. And what you know is that a diffusive term is going to regularize the things. So you say, okay, let's look to the problem with not 0 here, but a small term, dissipative term, which is written here. In that case, it's easy to show, and this is written here, that you have now a single problem, a single solution, which is given here. So, which was the first solution that I obtained, but without looking without introducing a dissipative term. And more important is that this velocity is independent of the diffusion coefficient, because this epsilon is a diffusion coefficient. It should be the dimension of a length square divided by a time to have the same dimension as this. So it is independent of the diffusion coefficient, the small diffusion coefficient that you have had in the equation. So so now you have a continuous function which, when epsilon goes to 0, which is written here, sketch here, go to the step function. Now you know from a mathematical problem, yes, this is a very delicate mathematical problem which was solved in the 19th century, end of the 19th century, by the mathematicians. So it's a pure truth. So And if you use in this equation, this was developed in the beginning of the 20th century. If you used, oh my goodness, if you use now a function u, which is just proportional to u, this is called the Berger's equation. And for this Berger equation, one obtains analytical solution of the initial value problem, but not only showing that the asymptotic propagation velocity of a bump like that is effectively this expression. So now the problem is completely clear. Now, what did Riemann? Yes, he gave much more important result. He was solving the real Euler equation with a constant entropy and an ideal gas. So working with constant entropy and for an ideal gas, he solved he was considering the Euler equation. Okay, so this is mass conservation, one-dimensional. He solved that in one-dimensional. This is mass conservation, and this is a momentum conservation, and this is a pressure term when you used the constant entropy approximation. In such a way, you can express directly the pressure in terms of the density through the propagation, through the speed of sound, a square, which is the derivative of p relative with respect to rho at constant entropy. And this is this term. So this is the Euler equation that Riemann was considering. What it is very simple. He multiplies the first equation, the mass conservation, by lambda. So you multiply this equation and you add the two equations. Let's say Riemann proceeds in a different way. I am presenting a much simpler way to obtain the Riemann result. So just multiply the mass conservation by lambda and add the two equation. Good. Now, choose a lambda. Excuse me. Choose the lambda such that this term is just equal to lambda times this term. So in such a way now, if you used a particular lambda here, which is a factor that was arbitrary here, now you choose this one. If this one is when you solve this problem, excuse me, excuse me, this lambda has this expression. In that case, when it has this expression, this combine addition, this solution equation here takes this form when you obtain the same coefficient here on both sides. So that it's clear now that this describes a propagation along a line which is dx over dt equal lambda rho plus u. And this lambda rho plus u, because lambda rho is plus or minus a, so you have two possibilities, and these are called the characteristic equation. These characteristic equations are trajectory that propagate in the flow at the sound velocity relative to the gas in one direction and in the opposite direction of the flow and in the same. So you have the two solutions that are the two characteristics. So now the invariance that you have take this form, and so that you using this expression here for the invariant, you obtain the two conserved quantity. Excuse me. Where I okay. Because now, if you use this expression, you obtain this conservation quantity, and by using the conservation, the entropy, the constant entropy, which is written here, you obtain that the quantities that are constant, that are constant along the two characteristics here are respectively G plus, which is 2 divided by gamma minus 1, the speed of sound, plus U, which is constant on C plus, and the other is constant on the other C minus. Now, let's consider the case of the simple waves. In that case, for example, when you consider a piston, when we consider a tube filled by a gas and end up on one side by a piston, and when you start to propagate the piston downwards, downstream, excuse me, downwards, doesn't mean so you see, you have the piston here, and then you, and the gas is here, and then so you have a rarefaction wave, and for this rarefaction wave, these characteristics are constant, are straight line. On the opposite, when the piston move towards the fluids, now the characteristics, and this is going to explain the wave breaking is the formation of the shock. The characteristics, you know, here are the characteristic in the initial mixture. This is the trajectory of the piston, which is going to propagate towards the gas, and because of the slope of this characteristic is increasing, so that the characteristics are going to cross each other. But each characteristic propagates a different value of U. So you are going to have a point here where you are going to obtain a multiple value problem. So it's going to explain the formation of the wave breaking. So centered waves centered waves are particular waves that are very simple configuration. The first one is the piston is 0 for negative time, and the piston starts to move with a constant velocity at t equals 0 for t positive. So these solutions, it's easy to show that they are self-similar, and in that case, you have the formation of a shock here. Where it is? Okay, here, this is very simple. This is a trajectory of the piston, and this is a trajectory of the discontinuity here, which is propagate upstream the piston at a faster velocity than the piston, so that the flow, the length of the column of gas, which is put in motion, in front of that it is at rest, is increasing linearly with the time with the velocity, which is the difference of the two velocity here. On the other side, so this explains by the Riemann construction, this explains the formation of shock that I have described in my first slides. And on the opposite, when you look for a piston that propagates in the opposite direction of the gas, you have the rarefaction wave, and this rarefaction wave, you can solve the problem completely in that case when the velocity is constant. And this rarefaction wave, there is no discontinuity of the velocity. The velocity is continuous, but not its derivative. The derivative is discontinuous, but not the function. So now this what I have just explained are the, let's say, basic elements in mathematics to understand the formation of shock waves. This is, I think it is, you know, when I was young, this part that I have just presented now was clearly presented in the program at school. But now it's no longer the case. So this is why I insist to spend 3/4 of hours to recall the basics, this elementary developments that are essential, in fact, to understand the physics of the shock formation. Now, let me go to a much simpler problem, which relative to the jump condition across a shock wave. This was developed by two different people and two engineers, by the way. Rankine was a Scottish engineer studying a steam engine, and Hugonneau was a very young student of École Polytechnique in France, which is an école with, which at the beginning was built to educate officials. But it turns out that the Hugonneau official for essentially for the artillery and this at that time. But Hugonneau, this school was École Polytechnique de Palaiseau in Paris is a famous school in France. It's still a famous school in France, but now it's no longer a school for military purpose. It's an engineering school. It's the best engineering school in France, in fact, and the most difficult one to enter. So this was Hugonneau. Both Rankine and Hugonneau find out a very, very, Rankine did not realize that, but Hugonneau realized that there is a conserved quantity that is very helpful to understand the jump across a shock wave, which is the total energy. So Hugonneau was the first to, realize that in addition of the momentum and the mass, there is the energy which is conserved. But the energy now is an energy which includes not only the internal energy, but also the kinetic energy of the gravity of mass of the fluid particle that you are considering. So, now in the modern language, the total energy that I have, the balance of total energy that I have described for you in my second lecture, I guess, takes this form where H is the enthalpy, U is the flow velocity, and this is the heat conduction, and this is the viscous effect. So this is a conservation form of the total energy. Now it's considering a discontinuity, or just let's say a transition zone between two states, one characterized by the subscript U, the other characterized by the subscript M, the both of them being uniform on the both sides, and propagating with the velocity d in the initial state, that when you are sitting on this discontinuity, you see the flow, initial flow, arriving with the velocity d, which is given for the moment, and flowing out from this discontinuity with the velocity un. Now, mass conservation, which is here, can tell you that rho u is constant, so the rho ud is called rho n, because what you want to know is what is the relation on the property of the gas on this side compared to the initial state, knowing the propagation velocity. So first relation tell you that there is mass, the mass flux is constant, which is written. The second tell you that when you integrate from one side to the other, assuming that the states of the gas in both sides are uniform, the time derivative here doesn't give zero. So the viscous effect disappears in the conservation of the momentum, and in the same way, the diffusive, the heat conduction and the viscous effect disappear from the jump obtained by the conservation of the total energy. This is the work of Hugoniot. Rankine did, you will find what did Rankine did in my book. I tried to explain that in my book with Jeff Sirby in 2016 book. You will find that, the detail. I will not explain here what Rankine did. It was a different approach. Now you can integrate, you can write simply this equation here for the momentum conservation, introducing the mass flux. Introducing the mass flux, the mass flux is the same thing when you know the initial state, that is the same as the propagation. Is this completely determined by the propagation of the discontinuity. So this is written here. The same, you can write now the jump of enthalpy here, and it's a matter of simple algebraic to write this in this, using these two equations in this form. And this is what is called the Hugoniot curve that relate, that is expressing in the jump condition in the diagram P versus the elementary, the unity per unit mass volume, which is 1 over rho, 1 over the density. And this line here, so this is the conservation equation, and this one, which use the 2, and this is simply called the Michelson-Rayleigh line, which is this equation here. So you have one curve for P over 1 over rho that describes the conservation of the total enthalpy, and the other, which is a straight line in the plane P versus 1 over rho, which is a specific P versus a specific volume 1 over rho, which is a straight line, which is called the Michelson-Rayleigh line, where the slope is the square of the mass flux. Okay. Now you can put this in an elegant form. It is surprising that I never found this simple expression that I'm going to show to you, which is written here. When you introduce these two quantity for the pressure jump and for the jump of volume, specific volume, 1 over rho minus about 1 over u, which is reduced. So this is a reduced expression of the pressure jump. This is a reduced expression for the specific volume, 1 over rho. If you use this form, you obtain the Hugonot curve in the form of an hyperbolic equation P versus rho, nu. And the Rayleigh line is, I never found that before. It looks to me that I was the first to write in a so simple way the Hugonot curve in my book, but I am not sure because it's so trivial that. So when you put this is easy. What time is it? So I will stop in few seconds. When I introduce this linear relation here, I obtain a quadratic equation either for rho or for p. This is the same thing, and this tells you, this equation, when you solve this quadratic equation, tell you what is called the jump condition. The jump on the compressed side of the shock is called the Neumann state, and this is expressed easily in terms of the Mach number of the propagation, which is simply d divided by the upstream flow, upstream, excuse me, mu, tell me, excuse me, I am getting tired. I am getting exhausted. mu is simply d divided by the acoustic, the velocity, it is called the Mach number, propagation Mach number, which is a propagation of the velocity of the discontinuity divided by the speed of the sound in the initial mixture. And then using this relation here, you obtain this simple relation for the velocity, the pressure, the temperature, and the Mach number also on the compressed side compared to the Mach number on the fresh mixture. Okay, so now it's time to have a 10-minute breaks. So let's stop the lecture now, and I start again in 10 minutes. Thank you very much. So
thank you, Professor.
Okay. All right. So before the break, I was explaining that the conservation of mass momentum and total energy across the wave, the shock waves, is obtained as by the intersection of the Michelson-Rayleigh line in the diagram, in the plan P, diagram P versus the specific volume. This is the initial point. This is U, and this is the burn. Oh, excuse me. Is the compressed side of the shock, and it is obtained at the intersection of the Hugonot curve and the Michelson-Rayleigh line. So, here are the jump obtained in terms of the propagation velocity of the shock, or more particularly the Mach number, which is the ratio of this propagation velocity divided by the speed of sound in the initial mixture, in the important mixture. General comments are worthwhile than no. The first is that Hugonot curve is tangent to the isentropic curve. This is not, it is not written here, but this is important to know. And it turns out that the Hugonot relation is not an isofunction of state, which means that you cannot write this Hugonot relation here, which is written here in the original variable, as a function simply of two quantity 1 over rho p in terms of the initial condition. It cannot be written in that form. So it is not an isofunction of state, as is, for example, entropy, energy, and so on. For an ideal gas, excuse me, okay, this is okay. No, okay, I did a mistake here, but it is not a problem. All right. What I have to say now is that a rarefaction, you know, the entropy from the fresh mixture, the entropy of the shock gas is necessarily higher than the entropy in the initial state. So when the wave propagates, the entropy of the gas is increasing, and in such a way that there is no possibility of rarefaction wave of finite, of constant size, like a shock, because the entropy will be decreasing, and this is against the it's not possible because the evolution should be irreversible. Okay, let me now just discuss briefly an important point concerning what is the inner structure of a shock. You see, the inner structure of the shock could be obtained when you take into account the diffusive effect and when you integrate this function in the conservative form. This is what, in fact, what Rankine did without the viscosity effect. He did that only for the conductivity. So let's work in the reference frame attached to the shock. So the first equation, conservation of momentum, tells you that across the shock, this quantity should be constant, and now you keep the viscous effect, and according to the conservation of the total energy, this quantity should be conserved across a shock propagating at a constant velocity. Use the boundary condition, no problem. So you have to solve. I skip the detail. You have to solve this problem. Here the problem is posed in the non-dimensional form. It turns out that you may easily anticipate what will be the order of magnitude of the shock thickness using simply dimensional analysis. You know, roughly speaking, looking to this momentum conservation, you should balance across the wave this quantity rho u square with this diffusive quantity. This is the diffusive quantity is a mechanism for going continuously from the upstream condition to the burn gas, to the shock, to the compressed condition. So, so this is an essential. So, in a sense, in order to obtain an order of magnitude of this thickness, you should balance these two terms. Or you may also do the same with this, but let's consider these two terms. Now, this term, rho mu divided by rho is a diffusion coefficient. So this mu divided by rho is a diffusion coefficient. What is written here? Something wrong. Okay, yeah. No, okay. Use, I guess that this is wrong because this is L. It should be length square, length over A. No, that cannot be. It's not. It's L. There is a mistake here. It should be a diffusion coefficient as the dimension of a length square by a time. So it should be L mean free path times A times the sound speed, because all the velocity are of the order of the sound speed. So you know the dimension here, and no, you know the dimension of mu, and if you balance the two, you find that the thickness of the shock should be of the mean free path. When you assume that the velocity, the order of magnitude of the velocity is the sound speed. So on that side, you have A square. On this side, you have L, A square divided by L. And so L, the length here, this is, okay, let me say that more clearly. du over dx is the variation of u divided by the thickness, okay? This variation of u should be of the order of A. So this, you have A square here, A here, you have mu divided by rho, which is the viscous diffusivity, which is L times A, so that this length here should be of the order of L, of the mean free path. So it turns out that just by the dimension analysis, the inner structure of a shock is not a macroscopic quantity, it's a microscopic quantity, which means that you should go through the Boltzmann equation and the kinetic theory of gases to solve this structure. This is true, excuse me, this is true except if the shock is weak. When the shock is weak, it is possible to use the macroscopic equations that are written here, conservation, that I have used. So in a sense, when you use this conservation equation, macroscopic conservation equation, to obtain the structure of the shock wave, at the end, you have a difficulty because it turns out that this thickness is going to be of the order of the mean free path, so that this equation has no meaningful, because these are macroscopic equations, while this thickness is microscopic. It turns out that there is a limit where the shock thickness is much larger than the mean free path. And this is when you have a weak shock. So it's this analysis that I am going to present here is what was developed by Rankine, except that he did not take into account the viscosity. So Rankine did not realize very well that what he was doing was limited for small shock intensity, which means that the Mach number, excuse me, the Mach number of the shock should be close to unity. This Mach, it turns out that the Mach number is all the time positive, but excuse me, all the time larger than 1. So this quantity is all the time positive, but consider the case where it is small. So it's, in a sense, it's a weak shock. So consider a weak shock. In that case, I have written here the equation in the general form, the boundary condition, and this problem now can be solved if you anticipate the order of magnitude of each term when this number here, epsilon, is small, that when this departure is small. So you are anticipating that you have such a relation for the velocity, for the jump of non-dimensional jump of reduced volume, specific volume. This is a relative jump of the pressure, and anticipate that in that case, this jump are for the epsilon. Now, when you do that, and introduce the non-dimensional length as the length, excuse me, scaled by the mean free. Where is my? Okay, by the length divided by scale the length by the mean free path, which is related to the thermal diffusivity like that. You obtain an equation which is valid up to a system of equation which is valid up to the order epsilon square written here. And using now the perfect gas law, it turns out you end up with an equation which is written here. This is a Prandtl number, which is the viscosity divided by the diffusivity, or thermal diffusivity. This is a Prandtl number for the unity. This is gamma minus 1. This is the derivative of the specific volume, jump of the specific volume, and you have a second order algebraic equation here. So this can be solved easily, and you one obtain here the solution. I skip the detail. You can do that by yourself. I don't. It's not necessary to spend too much time. It's straightforward. So the equation you end up, the reduced equation, is written here, which is dy, where y is a specific volume, d scale as it by epsilon to be for the unity. So dy is a quadratic term, and this is easily integrated, and you find that this the thickness of this is the mean free path divided by the small quantity epsilon, and so that the length, the thickness here is effectively of order of the thickness, excuse me, mean free path. The thickness here is of the order of the mean free path divided by this small number, which is a departure of the Mach number from unity. So, and yielding the confirmation that you can use the macroscopic equation to solve this problem, because you have a macroscopic length. But yes, as soon as epsilon become for the unity, that for example mu equal 1.5, for example, this epsilon is 0.5, and so the thickness is twice the Mitri path, and you cannot use to begin with the equation, the macroscopic equation that had been used. Okay, but this is to show, this is in fact what did Rankine-Hugoniot to obtain the jump that I have presented to you by using the Rankine-Hugoniot condition. Now let me go to a classical topic, which is also the Zeldovich-Neumann-Dering structure of a planar detonation. Now, how to, what is the simple configuration to understand what is a detonation? It's very simple. Do the same Gedanke experiment that I have talked about for the inert gas, but do the same now with a reactive gas. What happened is the following, is that, the shock in blue here, across the shock, the temperature increased, but the reaction rate, the exothermic reaction, which was frozen in the fresh mixture because the temperature was too small, behind this shock, the Neumann temperature is sufficiently high to ignite the mixture, and therefore the combustion developed behind. So simply, you can understand a detonation by this, in this simple way, in this simple configuration, where the velocity is put in motion at a constant velocity, like for a shock wave. Do the same for a reactive mixture, and you should have a wave here, which is constituted by a lead shock and a reaction zone. Okay, this problem was, it took one century to really understand the problem. Okay, from Abel 1870 to Dering and von Neumann, Dering and Zeldovich on the 40. It's most of, it is something like 70 years. Okay, now do exactly the same approach that we have developed for the shock. Now the only difference is that in the total energy, you have to consider the chemical heat, the chemical energy that enter into account, because it's going to evolve across the detonation structure. Now, so you do exactly the same problem that I have just discussed before, but including now this term for the heat, describing the heat release by the chemical reaction. Now you end up with a similar equation as before, but with an addition, for the pure shock, you have this without this term Q. This term Q here, capital Q here, is just the heat release divided by the enthalpy of the initial mixture. This is a non-dimensional number that describe the chemical heat release, the quantity of heat release per unit mass in the reactive mixture. And this number, capital Q here, is typically of order between 5 and 10, like that. So it's exactly the same problem as before, but now you have, the difference is that now you have a shift, and in such a way that the Rankine, this is in blue, you have the Rankine-Hugoniot condition for a pure shock. And when now you add this shift, which is due to the heat release, you have the green curve here. And then you have the same construction for the Michelson-Rayleigh line, because the mass conservation and the momentum equation are not changed. So the problem is the same as before. And you see, and this, what I am describing now, this is a very interesting point, was presented in a thesis of a young Russian scientist in 1893. So at the end of the 19th century is a thesis at Moscow University. So the man was very young, as was Hugoniot. Hugoniot was very young. He was 28, something like that. This was Michelson was maybe younger, maybe something on 24, 26, maybe 20, something like that. So these results were obtained by very young people. So, you know, this is very important to realize that the new result most of the time are coming from very bright young people. So just the geometrical construction, which is sketched here on this picture, this is the initial state. And in green, you have the final state described by this Hugoniot curve after heat release. And in blue is without heat release. You have just a shift. So you have the same construction. But now you have 2 points. This B prime point and this B point. So you have 2 solutions of this problem. And when the Mach number decrease, the slope is decreasing, and there is a marginal solution that I am going to describe later on, which is called which should be called the Michelson solution, but which is called the Chapman-Jouguet. But Chapman and Jouguet find out later after Michelson. I will be back to the minimum velocity, that is the Chapman-Jouguet velocity. Let's say that now let's try to understand the physics of this wave. First of all, is it possible to go solving this problem from the fresh mixture to the burn mixture going from here to here? It's easy to show that. I will explain that in more detail in the following slide. It is not possible. You first have to go to the Neumann state, which is you have first to go to an inert shock and then back to this state of the burn gas. Why it is like that? It is because the reaction can develop only when the temperature is strong enough. So here the temperature, and this will become very clear, there the temperature is so small in the initial condition that you cannot ignite the mixture. So this is impossible to go for. But if you go through an inert shock first, then the temperature has increased sufficiently to develop the reaction, to obtain a reaction rate which is non-negligible, and then you can go back, attain the burn gas. And it turns out that what is written here and it is a consequence of the large Arrhenius factor, saying that the reaction rate is negligible at small temperature rates, as I explained in the first lecture. So you have to go from the initial state U to the Neumann state B, and then back to the steady state. And this was understood by a chemist who wrote a very small note explaining that, because, you know, from a physical point of view, how to explain if there is no piston, as we are going to describe later on, how could you explain that a wave is propagating with a velocity larger than the sound speed to transform a mixture in an unreact mixture in burnt gas? You know, so this looks impossible because the velocity of the molecules are smaller than this velocity. So this was a very difficult problem, physical problem to understand at the beginning of the 20th century. And Paul Vièvre was the one to anticipate that this could be possible through the wave breaking, which was described by Riemann, mathematician Riemann, for an inert gas that increase the temperature and then start the reaction. So, okay. So here is this is the same picture as before, and now this is a zoom of this reaction. You have the shock, and behind the shock, the reaction rate start, the heat is released, the temperature increase. It turns out that it goes to a small maximum, and then you reach the equilibrium behind. Thickness of the shock is, as I explained to you, because the Mach number is going to not be small, is few. The thickness of the shock is of the mean free path, but the thickness of the detonation, the thickness of the detonation, where involving the reaction rate distribution, this is typically of a few millimeter compared to the mean free path, which is very, very small at that scale of a millimeter. Now, let me back to this construction of the Rayleigh-Michelson line, the Michelson-Rayleigh line, and when you decrease the Mach number. When you decrease the Mach number, this slope decreases like that, and these 2 points collapse in a single point, and this is called a marginal solution. It is not very difficult to understand that this wave is supersonic, just looking by the difference of slope, but I will not go into the detail. This is classical. And then now the question is, what is the characteristic of this marginal solution? Because below there is no solution, above there is 2 solutions, and you have this, what is called a marginal solution, which is called to Chapman-Jouguet, and I told you it should have been called Michelson. Okay. And the critical point, the essential result noticed by Michelson is that the flow relative to the lead shock of burnt gas is exactly at the critical, at the marginal solution, is exactly equal to the sound speed. while for all the other, the flow is subsonic. So UB here is smaller than the sound speed, and it increases, and it becomes equal to the sound speed at the marginal solution. And this is going to explain that this solution is self-propagating and can propagate without being sustained by a piston, as it should be the case for all the other detonation that are regime that are called overdriven detonation. As soon as the piston, you know, in a sense, I will be back to this point, stop the piston and look to what happened. If you stop the piston, the wave here is going to decrease, to decelerate to the marginal solution, which is the CG solution, which now is self-propagating, does not need the propagation. So this is a classical picture of the planar detonation waves. And yeah, now this now Zeldovich in the 1940 solved the profile of solved the inner structure of the detonation by assuming what was anticipated by Viel, that you start from a shock. The first point is that the reaction rate given by an Arrhenius law is much slower than the collision rate. And now, because the flow velocity at which the particle of gas are separated from the shock is typically of the order of the speed of sound, it turns out that the thickness that you obtain for the reaction zone is much larger than the thickness of the inner shock, which is a mean free path. So now you have so the detonation, the reactive gas behind the shock can be described by a macroscopic equation, continuity equation of fluid mechanics of reactive mixture. So this was conjectured. In fact, Viel did not understand that. Zeldovich understand what I am going to, and I just state that the diffusion rate is much smaller than the reactions rate, so that this is for the same reason that is written here. This explaining that the profile, this profile could be obtained without the viscous effect. But you see, viscous dissipation effect, viscous or conductivity are negligible by in the equilibrium of the convection term on the convective flow here and the reaction rate. So in this balance, diffusivity, because of this relation here, diffusivity does not play any role. So in order to solve the flame structure, it's no longer necessary, the detonation structure behind the shock is not necessary to take into account the dissipative heat conduction and viscous effect. Simply the profile results from the convection, the convection flow, where convection of particle of fluid which are reacting. Because when the fluid move downwards, it reacts, and so that the temperature increase. And this profile is just obtained by this balance. So you do not need any diffusive effect in the behind the shock wave, behind the lead shock here. It is clear, in a sense, that all the diffusive effects are quite necessary to explain the structure of this lead shock, but not to explain, to describe what is developing behind. I will skip the detail now. So what you have to solve are the Euler reactive equation, according to the voltage. And so there are many details, but I will not enter into the detail here. You find that in my notes or in the book, but in the notes, it will describe here completely. And what is interesting is the following, that you end up with an equation, which is written here, which this is a psi is a progress variable, which tell us what is the fraction of the total heat which is released. You see, this, and now you can express the flow velocity u square, how it increase, how it evolve with this term psi here, which is simply what is called the progress variable. As I told you, it is simply the fraction of total heat which is released. So you have this equation. This is the total heat released per unit mass, and you have this equation u square, a square. You know this, and now it's clear that you are going in this space u square psi. You are going to have a turning point when u equal a, and the picture is here. You see, the picture is here. When you go from U to B, if you start from B, you integrate B, from the Neumann state, just behind, you integrate to go to B. This is this branch of the solution here. Excuse me. Okay, this is his branch of solution here. I go from this point here to the equilibrium state, which is here, and this in this state, because it is subsonic, this the u is smaller than psi, the slope here is still positive. So you have this side. Now let's continue to solve this equation. So you have this, and you arrive at a term, at a point which is non-physical, where a equal u. Now you change, you have a slope, you have a vertical slope, and so the solution is turning back to this point. And in a sense, if you want to, when you are asking the question, is that possible to go from the initial condition to the burnt gas without going to the shock, you should use this branch. But this branch is non-physical. Why? Because the reaction rate is 0. So you cannot explain u square in terms of psi. So, and this is now clear when you decrease the Mach number here. So you decrease the Mach number, the velocity of the piston, if you like. You decrease the velocity of the piston, and now when you reach this point here collapse here, where the slope is vertical. Okay, so you have a full picture here in the diagram u square times the progress variable, explaining why you should go first, as anticipated by VL, to the shock, inert lead shock, to then reach the burn gas. All right. Now let me finish. Okay, 21. Let me work 10 minutes more. Let me now go to describe this Chapman-Jouguet wave and to explain in more detail why this Chapman-Jouguet wave is self-propagating. I have recalled here the diagram written for the velocity in the relative, excuse me, oh no, this one. Here, when I sit on the detonation structure, I see the fresh mixture arriving with the velocity, propagation velocity of entering with the velocity. You know, now the propagation is from right to left. It is just the opposite of my previous slide. So you should be careful with that. So here, this is the lead shock. This is the reaction wave, the reaction zone here. When you are sitting on the shock structure, you see the fresh mixture arriving with the velocity and escaping in the burn gas with the velocity UB. Now, if you are in the laboratory gas, this structure moves with the velocity d, and now the flow, burn gas flow, is propagating is at the velocity d minus UB, all right? And when you are at the Chapman-Jouguet state, this UB here, excuse me, okay, this UB here reach, which is smaller than the sound speed, reach the value of the sound speed. This is the marginal CG detonation. Now, in this picture, I represent what happened when you have an initial overdriven detonation, and when you stop at a given time the piston. On the left here, this is my overdriven detonation. You know, the piston here is in motion at the velocity Vp, and the detonation here and the front is moving with in the laboratory frame at the velocity d. And and this now what happened is these are the velocity in the laboratory frame d, and the piston d minus ub. Okay, now when you stop the piston, this gas here close to the piston, the velocity should go to 0. But now you have to go through 0 to a non-zero velocity. This is going to be to occur via an expanding wave. Okay, and this expanding wave, and as all the expanding wave, the boundary of the boundary of the and this I will explain in more detail later on. The boundary of this rarefaction wave. I apologize. The words are in French here. This is a rarefaction wave. This boundary of the rarefaction move relative to the gas with the speed of sound in such a way that when you are in the in over-driven detonation, by definition, the velocity of this point here is larger than the propagation velocity of the lead shock. Therefore, this point is going to catch the leading edge. And when it catch, it catch and it decrease. When it catch, it slow down the motion. It decrease the motion because of the propagation, down to the case where the velocity of the propagation here, this decrease when this reach this, you know, the expanding wave slow down the overall the structure of the detonation, decrease the velocity down to the Chapman-Jouguet velocity. But at the Chapman-Jouguet velocity, the leading edge of the rarefaction wave is exactly, because you are sonic, the sonic condition is verified, it is exactly the same velocity as the leading edge. So that this structure here is self-propagating with a Chapman-Jouguet velocity, or say, in other words, the damping by the expanding wave in the burn mixture is screened by the sonic condition. So this continues to propagate at the Chapman-Jouguet velocity, and this is going, this point is going slower than this point, and so the thickness here is increasing. But the structure is completely preserved. So, okay, it's time now to have a 10-minute breaks. Okay?
Okay, Professor.
Okay, so I want to mention that this selection mechanism of the Chapman-Jouguet regime by the rarefaction wave behind in the burn, developing in the burn gases. This problem has been solved completely recently in a GFM paper in the limit, in fact, of which is not very realistic, but limit for which you may have analytical solution of the small heat release. So this for those, excuse me, where is my pointer? Ah, I lost my pointer. Okay, here it is. For those who are interested, you have a Journal of recent Journal of Mechanics paper where this problem is fully solved. You see, this is the final trajectory of the Chapman-Jouguet detonation. All right, let's go now to a very important problem in combustion, which is a problem concerning initiation of detonation. So I change slides. Escape. All right. Okay. All right. So now this is, in fact, it is the 11th lecture, I guess. Initiation of detonation. This is, before to discuss how to ignite a detonation, let me briefly mention how to understand detonability limits. It's very simple. In order that the combustion proceed behind the lead shock, the temperature at the Neumann state, that is the temperature of the compressed gas behind the shock, should be larger than the crossover temperature that I have presented to you yesterday, which is controlled by the chemical kinetics. So this is what is going to define what is called the detonability limit. It is written here. So the crossover, the temperature of the Neumann state of the Chapman-Jouguet wave should be larger than the crossover temperature. If it is not the case, the no detonation can propagate. And this, usually this crossover temperature is between, let's say, 1000 Kelvin and 1200 Kelvin, something like that. And this gives you the composition that which is required in order to have a detonation. All right. Now, the problem of initiation of detonation is a very important problem from many points of view. For the applied point of view, it is essential for many problems of safety, for example, but it is also a fundamental problem, which is essential to be understood in combustion. I will consider the three types of initiation. The first is called the direct initiation problem, which is the following. You liberate quantity of heat, of energy at one point in free space full by reactive mixture. And and the question you ask is, what is the critical energy that has to be deposited to ignite this a detonation? And another problem is was discussed by Zeldovich, which is called the spontaneous initiation of a detonation, which is associated with gradient of temperature that are built for coming from other mechanism. I will explain that later on. And the last one, not the least, but the most important problem I would like to discuss is the deflagration-to-detonation transition, which is a very important fundamental problem, which is not, let's say, which is still open. So let's start. To begin with, I have to just give some few information concerning the rarefaction wave behind Chapman-Jouguet solution. As I just present to you, this rarefaction wave is essential for explaining the selection of the Chapman-Jouguet solution. Therefore, when the Chapman-Jouguet propagation is propagating in free space, one-dimensional or spherical, you should have a rarefaction wave behind. And this rarefaction wave, it turns out that there are solutions, exact analytical solution of this rarefaction wave of the self-similar form, which meaning that the flow field U R T depend on R and T, space and time, only through the variable R divided by T. And this is called a self-similar solution. And this self-similar solution are very useful for the understanding of the rarefaction wave behind Chapman-Jouguet detonation. It turns out that the planar, I will consider planar and spherical, and that the two cases are different, essentially because of the different form of the Laplacian operator. So here again is a recall of the quadratic equation defining the final state. And here are the sonic conditions. And it's what is useful is that to recall that when the Mach number, that is, once again, the propagation velocity of the wave divided by the speed of the sound of the unperturbed mixture, when this number for the Chapman-Jouguet at square is larger than 1. And in that case, and this works very well because this Mach number is between, let's say, typically is something like 4 or 5. So to the square, it's something like 25, for example, it's larger than 1. In that case, you have a very simplification that appears immediately, and which is useful. Excuse me. Where is my? Okay. That you can see here that for example, this expression of the specific volume, reduced specific volume at the in the burn gas of the Chapman-Jouguet, this is 1/2, for example, -1/2, and the velocity u of the gas is simply the Chapman-Jouguet velocity divided by gamma plus 1. So this is simplification that are not essential from a fundamental point of view, but helps a lot the calculation. So let's look for a self-similar solution of this problem in this limit. Let's start with the planar detonation. So the planar geometry. You see, when you have a self-similar solution, when you look for a self-similar solution, the partial differential equation of the Euler partial differential equation become ordinary differential equation just by the change of variables that are recalled here. So, okay. So here now are the Euler equation in planar geometry, ordinary differential equation, which is obtained by using the self-similar form. And it's easy to show now that putting together these two equations, eliminating the d rho over dx, that the equations you obtain as this form here, okay, in such a way that the solution is this term should be 0, okay, factor. So immediately you see that the profile is linear in X. So you find immediately the profile of the velocity, or not the velocity, this is the density. No, excuse me, this is the velocity, which is, be careful with the notation. Huh? This URT is written as this strange V function of the self-similar variable. So it's clear that this is linear in space. Now, using the Riemann invariant that I have explained in the previous lecture, you find out, and using the sonic condition, you use the sonic condition at the burn gas of the Chapman-Jouguet, so the Chapman-Jouguet, you find out the complete expression for the equation of the rarefaction wave, which is a straight line. And using the different results that you have here, it turns out that this where is my pointer? Here is my pointer. Yes, this is a straight line, and it turns out that this straight line reach zero at 1/2 here, which is where this on this axis you have this self-similar variable divided by the sound, because this variable has the dimension of velocity, and to make non-dimensional, you divide by the propagation velocity of the Chapman-Jouguet. It turns out that in this frame, the propagation, velocity, this velocity divided by the Chapman velocity divided by gamma plus 1 is 1 in the burn at the CG wave. So here, this is a CG wave, and the rarefaction wave is a straight line. So it turns that immediately you see, and this is a very important point. No, where is my pointer? Oh, okay. And it's easy to show that this point is called a weak discontinuity, the point that you have here. Where is? All right. This point is a weak discontinuity, meaning simply meaning that this point propagate that not only that you first, let's say you have. Okay, you have a core. Okay, you have a core of burned gas at rest, and this core increase the radius, or this is not a radius because you are in planar, but it's the thickness of this core of burned gas at rest increase linearly with time, because this point corresponds to the propagation velocity of the leading edge here at the sound speed of in the burn gas, and this, and it is and when you have a change of slope in a temperature profile, this is called a weak discontinuity and should propagate with the sound speed of the in the gas, should propagate relatively to the gas at the local sound speed, as all the, because of the nature of the weak discontinuity. So this is a picture for the planar detonation. That's clear, all right. Excuse me. What's you know? Now, same problem in spherical geometry. This is a little bit more tedious to consider, and you have to go through numerics, numerical simulation solution of the profile, because you know, the only difference, the new term that you have in this equation compared to the planar case is that, and this term is coming from the divergence. You know, the divergence in spherical give you this term here when you use the self-similar form, which is a new term relatively to the planar case. And this play, I wonder if there is an error here. Okay, forget about it. You are going to check that. But now, this is okay. This solution was obtained. It's called a self-similar solution of the first kind in the work of Zeldovich-Barenblatt. There are an excellent book on that. And here are the equations that you have to solve. And you cannot solve at the difference of the planar case, you cannot solve that analytically. You have to go through numerics to solve that. And what is very important from a physical point of view is the following: is that the slope here in the burned gas just beyond the CG wave is infinite. So this was, you know, Taylor was very concerned by that, because, you know, this solution is obtained assuming that the Chapman-Joulet solution is infinitely thin. And he said, how is it possible to have an infinitely thin structure here followed by an infinite gradient? So this he realized that the solution, this self-similar solution of spherical Chapman-Joulet wave, when Chapman-Joulet detonation, when the inner structure of the wave is neglected, is not completely relevant. There is something that difficult to understand that. And, all right. Just I have said that what you have to do to integrate numerically, it's just every student can do that with their laptop when they know how to integrate. You have to start the numeric from, you can do that as an exercise. Huh? I am not able to do that because I do not know how to handle the numerics, but I am sure that the students, that most of the students know to do that. So you have to start from here and to integrate background and to stop the calculation when you cross, when you reach a zero velocity here. And then you will see that not only the velocity is zero, but the tangential is also zero. So this is a nice solution, a nice mathematical problem. Okay, so you once again you have a spherical kernel. Is it? Where is it? You have a spherical kernel of burned gas at rest whose radius increase linearly with the time behind the wave, the spherical Chapman-Joulet wave. Okay, good. Let me now just recall briefly what is a blast wave. A blast wave is a problem that you obtain when you deposit energy, punctual energy in a free space, and when you deposit a finite quantity of energy instantaneously at a point in the free space. And so you are going to disturb, this is going to disturb and to create a flow, and this flow is called a blast wave. Okay, I will skip the detail. This problem was solved, apparently it was published by Taylor after Sedov, but apparently Taylor has said that the publication was in a report which was confidential because clearly this was related to the atomic bomb during the war. But it's, you know, apparently Taylor did the calculation in 41 and set off later on. But this is not clear because the Russians also were very concerned by the bomb, so it's not clear that people like Zeldovich and Landau also did not solve this problem. So the simplification which is useful also to attack this problem is to consider a strong shock. It's clear that at the beginning the shock is very, very strong. So and you look for a self-similar solution, and okay, let's forget the details. Simply, in this problem, the only dimensional quantity that you have is the energy that you have deposited and the density of the fresh mixture, and density and in such a way that if you have to build, now what you want to know is that you are going to create a spherical shock wave that is expanding, and you want to know how the radius is increasing. And you see, only simply by dimensional analysis, you can anticipate such scaling here because of dimensional analysis. There is no other way to create a radius with E and rho u and using the time. So that's the only way. And now the problem is to find the coefficient here. And here is the velocity. You see the velocity decreases with the time, like 1 over t 3 over 5. And this exponent is only can be only obtained just by dimensional analysis, nothing more. But now what is difficult to obtain is this coefficient here. So, and B is obtained when you conserve energy. This, forget about the detail. And here is a structure that you obtain in such a way that when you know, for example, the trajectory of the lead shock, you know the energy which is liberated. And this was useful for the experience in the atomic bomb, because you record the trajectory of the radius of the shock in terms of the time, and in such a way you can compute by this factor here. You can verify this relation first, or this relation, and compute this B, and not compute this B. This B you compute numerically, and you can now have an experimental measure of the energy which is released. Good. Now let me consider the problem of direct initiation. So now the problem is, okay, I begin by the same methods that I have created blast wave, but I do that now in a reactive mixture. And the question is, when do I ignite a detonation? It turns out that this problem, the successful direct initiation, is a transition between two self-similar solutions. To begin with, the heat, which is the heat released by the chemical reaction, because the volume is so small that this, and so the quantity of heat which is released by the chemical is negligible compared to the deposit energy, E. So you should start with the blast wave explosion solution of Sedov-Taylor. And now, if you succeed the initiation, and in the long time limit, you should end up with a spherical CG wave with a self-similar solution that I have just described. So a successful direct initiation is just the transition between two self-similar solutions. Now, it turns out the experiments show that when the energy is not sufficiently large, you do not go to the spherical CG wave, you go to zero. You go to a weak, sonic, an inert sonic wave, which the velocity go to the speed of sound. So here now, people solve this problem numerically by considering the detonation by neglecting the inner structure of the reaction wave. In that case, you consider the detonation as a discontinuity, zero detonation thickness. In that case, there is no critical energy. Whatever for any energy which is deposited, you end up with a Chapman-Jouguet detonation. This, or more particularly, using the planar parameter d versus the radius of the lead shock. Okay, you start with the inert mass wave, and then when the radius becomes sufficiently large, you finally end up with a spherical Chapman-Jouguet detonation, where I have recall here the self-similar solution. So an important conclusion is that the critical energy, if there is a critical energy, what is observed experimentally, this is due to the modification of the inner structure, because when you neglect the modification of the inner structure, there is no you ignite every time. One of my PhD students, Lontin A, I think he was one of the first to develop numerics of this problem. Many others developed the numerics later on, but I think that he was one of the first. And this explains what the numerics show. I remember Lontin coming to see me saying, look, hey, professor, look what I obtained. I obtained very strange things that when here are, here you are the trajectory of the lead shock for different energy. This is the critical energy below which there is no ignition. And this is the marginal. And then, sometimes you have oscillation, and then you ignite. This oscillation that you have here is a natural oscillation for let's say spherical detonation, which is which I will explain that in the tomorrow. That is this kind of oscillation, but in a sense, now when now Zeldovich was the first, you see, excuse me, okay, you see here in this kind of, excuse me, okay, you have a critical radius here, okay, you have this is a marginal solution that I'm going to describe. There is a critical radius. It turns out that Zeldovich was computing this critical radius. Let's say he has a theory for that. Excuse me. Okay. This is not well he develops the following criteria here. He said, okay, for the detonation to be ignited, the criticality is obtained if the time of the blast wave to reach the Chapman-Jouguet is if this time is of the order of the reaction time at the moment state, because if this time is too short, you do not have time to ignite. When you develop this this criterion, you end up with a critical energy that can be expressed in terms of the critical energy, deposit energy, can be expressed in terms of the heat release per unit mass by the mixture, which is this expression here, and time, this, this is an energy volume per unit mass. Rho u is the mass per unit volume, and you multiply the volume that appear in the criterion of Zeldovich. This volume is simply the cube of the thickness of the Schamann-Jouet detonation. Turns out that this is many orders of magnitude smaller, of the order 10 minus 5, 10 minus 6, than the experimental data. The best experimental data on this problem was obtained by John Lee in around 1985, something like that. So the conclusion of that could be, you know, this is very clever. The analysis of Zeldovich was very clever, but he never take into account the geometrical aspect. So he never take into account the curvature and this modification of the structure, the Schamann-Jouet wave. And this turns out to be an essential phenomena to obtain the critical energy, to obtain a good order of magnitude of the critical energy. So what when Lontin showed me this result, I was impressed by the quality of the numerical result obtained, that one can obtain. And I try to understand why this critical energy, this critical radius is much larger than the, in fact, than the thickness of the Schamann-Jouet wave. It turns out that around the 90s, I guess, Amable Lignan, who is a good friend of mine, who is also who is a great scientist in fluid mechanics and combustion theory, tried to say, why, okay, if I multiply the critical radius of Zeldovich by the reduced activation energy, then at the cube, because the radius for the critical energy occur like the cube of the radius. If you multiply by a reduced activation energy beta, which is about 10, you multiply the result by 10 to the 3. So you approaching the order of magnitude of the experimental data. But so what we did with Lontinet is we solved the problem for nonlinear curvature effect of spherical CG detonation by assuming that now that the inner structure is curved but quasi-steady. And when you do that, I will skip the detail. You see, you take out all the unsteady effects. You keep only the curvature effects that appear here, in fact. Let me show where they are. You know, the curvature effects are here. This is divergence of the flow, you know. Now, if you assume that the radius, that the thickness is smaller in front of the radius, that you anticipate that the critical radius is larger than the detonation thickness, you may take this out. So you reduce the problem, and when and using a very simple model, which is called the square wave model, which this is very dangerous, this square wave model, to describe unsteady effect, as I will explain that tomorrow. But for the quasi-steady phenomena, it's not a so bad model, and this model is just recall here. You have and you assume that the heat is released instant, let's say, in a very short time compared to the induction time. So you have this kind of structure. And when you do that, you can compute the critical energy. Let me skip the detail. And in fact, you find by this analysis, you find an equation between the radius and the velocity of a curved frame, a spherical frame in quasi-steady state approximation. You find a nonlinear equation for, it's this kind of nonlinear equation is typical in combustion, because this term exponential is coming from the Arrhenius factor. So this d is the velocity, propagation velocity of the spherical detonation, and Rf here is the radius. Cg is the reference of the Chapman-Jouguet, and beta n is the large activation energy. And it turns out when you look to this nonlinear equation, that you have a turning point when you express d in terms of r or r in terms of d, that there is no solution below of this equation below a critical radius. And this critical value, by the way, is given here and is in good agreements with the experiment, good agreements in order of magnitude, let's say, with the experiments of John Lee. And also with the direct numerical simulation of Lontin. You see, this has on the right is the direct numerical solution of Lontin here, and here this, and you can evaluate the critical radius, and in fact, and compare to this analytical expression in black, and it works very, very well. So at that time, we were very excited because because it solves the problem of the critical direct initiation. Because this is the critical expression. The difference with Zeldovich is that you have the activation energy here, but in addition of that, you have a small term in the denominator and a large term in the numerator here. So this radius is of order 1,000, and so that you recover the correct order of magnitude of this. So this we were very, very excited with this result. However, there are strong limitations of this analysis. The first is a square wave model, and the other is a quasi-steady state, because this is sketcher, this is to recall. You see, this is what you, this is now this is what we obtained more recently when looking to the trajectory. when looking to the trajectory, we find such trajectories that you cannot, for the detonation, you cannot reach, you have a turning point. So we said, okay, this is a quenching, should be describe a quenching. But this is not very satisfactory because everything is quasi-steady. So when you have a condition like that for quenching and so on, you should not be quasi-steady. So the quasi-steady state approximation was a weakness of the analysis, and the analysis was criticized at that time by many people, but I guess they were jealous that we obtained the right order of magnitude of the energy. The problem, you know, many people thought that what is important is to find the exact value of the critical energy. Before to obtain the exact value, you should obtain first the right order of magnitude. So we were very excited, but you see, for example, in our original paper, we have already mentioned that in fact it is not quite satisfactory, even if the order of magnitude are correct. Look, you have sometimes unsteady trajectory that should ignite, but unsteady effects lead to a quenching. And also what I did not, sometimes it's you have below this, you obtain an up reignition below. So in a sense, all right, we have a good correct order. Something very difficult should appear around this critical point. And this is the next study that we have, is a study that we have performed much more recently to take into account of this unsteady effect near the criticality. And this is what has been published recently in the GFM paper, which is just appeared. Raúl Hernandez is a PhD student, and Bruno Denet is a numerician in my institution, and we have been able to find an asymptotic analysis in the small heat release. That you see, when you are talking of detonation with small heat release, an experimentalist could tell you, but this is nothing. There is no detonation with small heat release. That's true. But it turns out that the asymptotic analysis can describe properly the interaction and the curvature that have been obtained before with unsteadiness. So, and not only that, but most of the conclusion could be useful for real detonation with a non-large, non-small heat release. The same thing occurred when Sivashinsky was describing the cellular structure of the flame, non-linear cellular structure of the flame by using small heat release. And it turns out that this analysis contains the essential phenomena that occur also for large heat release. The point is that with small heat release, you may have an asymptotic analysis, and so that you may get a physical insight of the problem that you cannot obtain, for example, even with a pure numerical problem. This, in my experience, in my life, in scientific life, I know working with good people in numerics that you need, when you are doing direct numerical simulation, you need insight coming from asymptotic analysis, even if they are not in the exact range of the calculation. So, in fact, there are two papers that appear in GFM that last year and this year. You see, how many times? Oh, I have to stop in 3 minutes. So I will just briefly say a few things. You see, the analysis that we are going to use is that the Chapman-Joulet velocity of the planar detonation is close to the sound speed because it is release is small. So this is a small number that is very useful to obtain analytical expression. And so this, and we are working near the Chapman-Joulet solution in such a way that we are considering detonation, velocity that are close to the and this number is of order unity or smaller when you reach the Chapman-Joulet velocity. It turns out that the first result we obtained, analytical result that we obtained, was concerning the rarefaction wave of the Chapman-Joulet solution of the Taylor, the analog of Taylor. Yeah, this Taylor was obtained in the opposite limit of a large Mach number. Here, the Mach number is close to unity. And here is a solution, analytical solution that we obtain, which is which has exactly the same property as the one obtained, the cell-similar solution obtained in the opposite limit. Namely, that the slope is infinite here. This is when this is obtained, assuming that the detonation is a zero thickness. But and working in this limit, you end up with you show that the cell-similar solution is at the same time is of the same type as in the opposite limit, which is much more realistic. So this gives you some confidence that this limit is meaningful. So I think that it is time to stop the lecture today, and I continue tomorrow. Okay?
Okay, Professor.
Sure, Professor.